We are down at Preston today, but he had something happened. I don't know, but all right, come on. So I will begin with a word of prayer. So here we go. Dear Father, we thank you for this day again. I thank you for the students. Just ask you to bless our work today, help us to glorify what we do. And we just thank you again, Lord, for your many blessings this day, Lord. In your name I pray, Lord Jesus. Amen. So we talk a little bit, and I really do just mean a little bit, about higher derivatives. But it's important because it helps you understand a little bit more about just how special what I'm going to talk about for the most part today is. So if we're given normed linear spaces V and W and a differentiable map, so we space V and W normed linear spaces, and F a mapping from, say, U, a subset of V to W, right? Then, of course, the differential at a point, supposing it exists, is itself a linear map from V to W, right? So that means then we can define, if we want, let's say big F prime, a mapping from U, supposing the F is differentiable on U, all right? From U to what? Well, that's the question. It's like, what is the derivative? Well, the derivative is a linear transformation. So for each point, we're actually assigning one of these things, right? So like F prime of A would be DFA in this discussion. But that's a linear transformation, right? So like this linear, our notation for that is, so DFA, it's an element of the linear transformations from V to W. So the derivative map is actually a mapping from U to linear transformations from V to W, which is quite different than Calculus 1, right? Because what is one of the first things we learn in Calculus 1 is you take a function, you differentiate it pointwise, right? And then the derivative function is again a what? You can define it to be a function again, right? So what I'm telling you here is that we start with a function from V to W, and the derivative is not another function from V to W. No, it's a mapping from, okay, fine. It's not a mapping from U to W. It's a mapping from U to linear transformations, right? That's really quite different than what we're used to. And so then we can go further. You can try to do, you can talk about what is the derivative of F. It's F prime, right? What if we differentiate F prime? What would that look like? Well, then we'd have something like this. D F prime sub A would be a mapping from V to the linear transformations from V to the linear transformations. This is starting to get really annoying, like that. So like the differential of the derivative map would itself be a linear transformation from V to linear transformations of V and W. Right. Now, fortunately, there's an isomorphism. This is like isomorphic to linear transformations from V to W. So we can we can identify these kinds of things with what are called bilinear maps. In particular, it looks like this. So I'm just going to write this formula down. We're not going to really do anything with this. It's just for the sake of like sightseeing, really. So f prime prime of h comma k, we would be talking about like df prime of a of h comma k, and that is meaning the differential of h mapping to dfh parentheses a of k. So to calculate a second derivative of a function on a norm linear space, we're up against this kind of jibber jabber. We actually have to look at the change in the assignment of the differential at each point, right, and calculate the differential of that, like so. So anyway, long story short, basically when you study this more systematically, and I'm not going to do that in here because that's not really what we're after, you end up with the viewpoint that to understand higher derivatives of a function of norm linear space, you end up looking at symmetric multilinear functionals. So what you end up looking at is like, it turns out that, if you're looking at like the nth derivative, you would be looking at, inputting like n of these in order to understand the nth derivative of a function. But this takes a fair amount of notation to build up, and I have zero intention of pursuing this further. So I just wanted to mention that this is what we're up against to try to calculate higher derivatives. It's actually somewhat complicated in the abstract. Yeah.
So df of a is a linear transformation.
Yeah.
Wouldn't that make differentiating it somewhat trivial?
No, because we're talking about the assignment. So like the assignment is not linear though. You see, yes, dfa for a fixed a is linear, but the assignment a maps to dfa, like this. It's not linear in a. Like if I replace a with a plus h, it's not the case that df of a plus h is df of a plus df of h. The way it varies from point to point is possibly nonlinear and kind of subtle. Now, the one thing I probably should prove in here, but I think I've done enough proofs in here so far, so I'm just going to claim that this is true if you guys don't mind. So like the main theorem we need about higher derivatives is just this, which is that if we have partial squared f, partial xi, partial xj, it's equal to partial squared partial xj, partial xi. In other words, partial derivatives commute. Now, in this context here, I'm talking about f like a mapping from, say, U, a subset of a norm linear space. Oh man, I just made that natural numbers. What's wrong with me? U, a subset of a norm linear space to like real, I'm talking about a real valued function. I guess I don't have to, excuse me. I don't have to assume real value. This is true for vector valued maps. Let me not, handicap us here. Because, we might as well claim the most aggressive version of this theorem since we're not going to prove it, right? Yeah. But partial derivatives commute. This can be proved. Well, we do need some assumptions. Like the precondition here is you need that the second partial derivatives exist and they're continuous. That is a sufficient but not a necessary condition. There are cases where the partial derivatives commute and yet the second derivatives are not continuous. We are not going to, delve that deeply. We leave that to experts, that kind of thing. Like, the question of what's the weakest context in which this identity holds is a difficult question. It is certainly true that if, here we're assuming that the second partial derivatives exist and are continuous on U. All right. That's the condition there. Okay, so just a warning, if we were to try to study higher derivatives, because you notice that we've defined the derivative for a function on norm linear space. We've got a bunch of theorems about it. It's natural to ask the question, okay, what happens when you calculate the second derivative? The answer is you get dragged into multilinear algebra. Because like it or not, the derivative is naturally the assignment of a linear transformation at each point. So, all right. So with that context, I will now talk to you about differentiation in an algebra variable. So in order to make sense of this section, I really need to first talk to you about what on earth an algebra is, right? So what is an algebra? A is an algebra over the real numbers if A is a vector space over the reals for which there exists a multiplication which we're going to call star. So star is a mapping from A cross A back to A again. This is called multiplication. And what are the properties of multiplication? So the only kind of algebras I'm interested in for this course and much of what I do research in are associative algebras. So like we want this multiplication to be associative. But before that, the algebra is assumed to be bilinear. So let me write down what that means. So like if we have a constant times x plus y, and we multiply it by z, we get, pull the constant out, x times z plus y times z. So we've got that. If we have y, I'll put the x first. If we have x times a constant times y plus z, we get the constant x times y plus x times z. All right. What else can I? Oh, it's associative. So associative looks like this. X times y times z makes sense. So I put the parentheses here. I put the parentheses there. So here I'm assuming that x and y and z are in the algebra and that c is a real constant. So the first two conditions basically just say that the multiplication works like normal, right? We can distribute across addition and in either way, right? Whether you got the addition in the first spot or the second spot, right? The third thing is associativity. What else? We'd also like to assume that our algebra is unital. We want to assume that there exists, let's say, 1 in the algebra such that that number 1 times x is equal to x times the number 1 for all x in the algebra. So this makes, so then A is said to be unital. A is unital. A unital simply means that there is an identity for the algebra, which I'm going to just denote 1 sub A here. Now when we actually get to an example, usually we end up just using the number 1 to denote the unity, but in the abstract, let's call it 1 sub A. What else? Well, let's see here, anything else? That's it. This is what an algebra is. An algebra is simply a vector space paired with a multiplication, right? If the multiplication is associative, we say it's an associative algebra. If there's also a number 1, it's an associative unital algebra. What would it mean for the algebra to be commutative, guys? What do you think? What would a commutative algebra mean? What would that have? We would have what? Like A times B is equal to what? B times A, right? For all A and B in the algebra. A lot of the examples I'll show you today are in fact commutative. All right? Let's see here. While I'm at it, let me, other thing, this is not part of the definition of algebra, but this is just fun to study for an algebra. U of A, this would be, let's say, x in the algebra, such that x inverse is also in the algebra where, like, you know, x inverse times x is the 1 in the algebra, and of course that's also x times x inverse, right? So in other words, U of A is the set of units for the algebra. It is the set of invertible elements. Those are the units in the algebra. And that's pretty familiar. If you think about number systems, we usually have units, right? Like any real number has a reciprocal. Any rational number has a reciprocal. Any complex number actually has a reciprocal, right? These are all number systems that we're familiar with that are examples of algebras where, you know, everything that's non-zero is a unit. But one of the really funky things about algebras is there's also these things called zero divisors. And so this would be something like x in the algebra such that there exists y in the algebra with y not equal to 0 and x times y is equal to 0. If you want, we could say or y times x is equal to 0. I don't really want to sweat it too much. I'm mostly thinking about commutative algebras, so whether it's a left or a right zero divisor is kind of immaterial. So this is weird, to have a non-zero thing that multiplies to give you 0, right? This is troublesome and different and new. All right. So without further ado, let me give you some examples of algebras. So example 1, and this is a kind of dumb example. If you just take the real numbers itself, this is an algebra because it satisfies these rules. I'm gonna have to buy some equipment. Can I get like a wall mount, like a no? All right. So this is an algebra. The multiplication is just regular real number multiplication. All right. That's example 1. Example 2, we can take the algebra of the complex numbers. So here we're looking at things of the form a plus ib, such that, you know, a and b are real numbers, and I squared is equal to minus 1. Complex multiplication satisfies the rules of an algebra. All right. Now here's where it starts to get weird. We can talk about hyperbolic numbers that have the form x plus jy such that x and y are real numbers and j squared is equal to 1. I'll write out the multiplication down here for you. If we have a plus bj times c plus dj, what is it?
What is that symbol?
Oh, I was trying to draw a funny looking h, but little script, capital script dh, yeah, for hyperbolic numbers. So the way this multiplies, we get AC, j squared is 1, so I get BD times j squared, which is 1, and then j times AD plus BC. It's a good thing nobody's trying to teach in this building. Golly. I swear. So, is it possible to buy a singing telegram? We should all contribute to send one over there.
We should buy a speaker that knocks the water out.
Yeah. So this defines hyperbolic number multiplication. All right. And there's other things about hyperbolic numbers that may be familiar to you. Like if I say z is equal to x plus jy, then the hyperbolic conjugate of z is x minus jy, right? So if you look at z times z bar, also known as z bar, you get x plus jy times x minus jy, which works out to x squared. You notice that you get the same cross terms. You get plus jyx minus jxy. So the cross terms, they be canceling, and you get minus j squared y squared, also known as x squared minus y squared. Now x squared minus y squared is just a number. So what this shows me is that z bar divided by x squared minus y squared is equal to 1, which then tells me that z times z bar over x squared minus y squared is equal to 1. What does this mean? Well, this means that apparently z inverse is actually equal to z bar over x squared minus y squared, which I will write out in a couple different ways. That's on the one hand x minus jy over x squared minus y squared. Of course, we could also write it as z bar over z bar, at which point you're like, oh, well, okay. Now, I don't know if you know this or not, but this is the same way we find the reciprocal of a complex number. Right? To calculate the reciprocal of a complex number, you simply calculate, like, the complex conjugate, and you divide by the product of the complex number and its conjugate, right? Like, I don't know if you know this, or maybe you've seen it before. Maybe it's been a while since you've seen it. But if I had like 1 plus, 2 plus 3i, and I wanted to calculate that, the way you do that is you do 2 minus 3i over, 2 plus 3i times 2 minus 3i, which ends up being 2 minus 3i over, 4 plus 9, which is 13, as it happens. I'll write it this way, though, to kind of emphasize a point here. When you calculate the inverse of a complex number, because the complex conjugate, in the complex case, if you have z conjugate, which is x plus iy times x minus iy, this is complex. What happens is you get a minus I squared, which is plus 1. So this ends up giving you like x squared plus y squared. So this is my complex corner, all right? I want to point out to you how different it is than hyperbolic numbers. See, hyperbolic numbers, whoa, dang. So hyperbolic numbers, notice this here doesn't have to be non-zero. See, x squared plus y squared, the only way for that to be 0 is what? If they're both 0, right? But x squared minus y squared, this is 0 when? Y is plus or minus x, right? So in fact, when we study this more carefully, the 0 divisors of h are actually of the form, x plus jy, such that y is equal to plus or minus x. All right. And fine, which you can actually show that this is basically it's the span of 1 plus j unioned with the span of 1 minus j. So this is like y equals x. This is y equals minus x. It's actually the two lines. The union of these two lines is a set of all 0 divisors. Those numbers do not have multiplicative inverses. All right, so some people would say, well, that means hyperbolic numbers aren't a number because number systems have to have inverses. Well, that kind of depends what you mean by number. I use the word number in a very abstract sense. For me, a number is just something you can add and multiply. All right. I usually assume associativity, but I'm open to the thought that you might not. So I don't expect you guys have ever seen these before. That's why I'm kind of slowing down here a bit to try to make sure we have some sense of what we're doing. Now, are there other examples of algebras? Well, yeah, absolutely. Like we could talk about 3 hyperbolic numbers. What do 3 hyperbolic numbers look like? So here's another example. Is this example 4, isn't it? 2, 3, 4. The 3 hyperbolic numbers, H3, I write these something like A plus BJ plus CJ squared. Here A, B, and C are real numbers, and J cubed is equal to 1. These are the 3 hyperbolic numbers. How many of you have already taken abstract algebra 1? Anybody? So a couple. You can take, so this is actually the real group algebra of the cyclic group of order 3. That cyclic group of order 3 being 1j, j squared in the current notation. So like example 5, if you have G as a finite group, forgive me, the rest of you who haven't had group theory, let's indulge the students who have for like 30 seconds, and then we'll be back. What's that? 2. There were 2. He exists. What are you trying to say? How rude. How dare you? Okay. You're trying to deflect away from your rudeness to the lack of my parenthesis. That was effective. I'll allow it. So if we have a finite group, we can form the real group algebra, which is, I think, denoted R sub G. And what that is formal linear combinations like x1, g1, plus xn, gn. All right, here, x1 through xn are real numbers. And the way you define the multiplication in the real group algebra is something like this. If I've got, the sum of, well, good grief. How to explain this briefly. Sample calculation, all right? If I have x times g1 plus y times g3, and I multiply it by z times g2 plus t times g7, whatever. The way the multiplication works is you just multiply coefficients xz, and then I've got g1 times g2, and then x times t, g1 times g7 plus y times z, g3 times g2 plus a yt, right? So what I'm doing is I'm just distributing. There's a clever way to write this formula, but it's not coming to my brain at the moment. But the point is, you can form this real group algebra simply by saying that you look at formal linear combinations of group elements, and the way you multiply them is assume that it just distributes like you want, and you just multiply group elements by the rule. You already know how to multiply the group elements, because if it's a group, then the way that works is that any 2 group things have to multiply back into the group again, right? So all of these things are, again, elements of the group. So anyway, sorry, I will stop that. So getting back to the 3 hyperbolic numbers, what does the inverse look like in the 3 hyperbolic numbers? Well, that's a mess. That's actually quite ugly to figure out what the inverse looks like in the 3 hyperbolic numbers as it happens. I don't know the formula for it right off the top of my head. If I happen to put it in the notes, I can write it down for you guys. But I don't think I did. I did write down the multiplication rule for it in the on page 57. But what I'll point out here is, well, I'm just going to tell you something. It turns out that the zero divisors, and this is not obvious, but I'm just going to tell you, the zero divisors of the three hyperbolic numbers are things of the form a plus bj plus cj squared, such that, how's it go? A cubed plus b cubed plus c cubed minus, man, what was it? Oh, I didn't write out, rats. Oh, man.
Would it have something to do with like things that are determined in the standard matrix?
Yeah, but I'm trying to avoid saying those words. A squared plus b squared plus c squared minus ab minus ac minus bc, I believe, equal to 0. So I can explain geometrically what's going on here. It turns out that the zero divisors of H3, if we think about this as the a-axis and this is the b-axis and this is the c-axis, the way it works, in this case, the zero divisors, there's like a plane of them, right? And that plane is a plus b plus c equals to 0. This is a plane of zero divisors. And perpendicular to that plane, you got the normal line, right? Normal line. And that's it. That's all the zero divisors in this algebra as it happens. Everything else has a multiplicative inverse. Now, if you want to understand this, you should study what Shane is talking about, the regular representation. You should like reformulate these things as matrices. Then you can basically use the theory of determinants to find formulas and things. But anyway, I think that's just enough to be dangerous, right? So these are some examples of algebras. And so now I'm going to tell you what we mean by a function being differentiable. All right, so the thing is, the algebra that I'm looking at, these are all finite dimensional vector spaces, which means we can give them a norm. So we can think of the algebra as being a normed linear space. And if we do that, we can think about a function being a mapping from an algebra back to itself again. So look at a function from an algebra to the algebra again, where A is a normed linear space. All right, then we say f is a differentiable at P in A, if and only if f is for Shea differentiable at P with differential df sub P, right? Which is linear and has the following property. Here it is. So what we have is dpf, all right, of, let's say, v times w, dpf of v times w, it has to be equal to, sure, follow my notes, dpf of v, I'm sorry, I'm sorry guys, at this point in the notes, somehow the p has shifted. So, I'm sorry, my p has somehow shifted from here over to here now. There are two different dominant notations, and sometimes people put a p here, sometimes people put a p here. My notation inexplicably has shifted, but I'll keep it right on the board since, my point is, I'm sorry if I'm not consistent with the notation all the time. I do try. I sometimes fail. So this property that I just wrote down is, you can also call the, this is right a linearity. In words, we can pull out a multiplication in the algebra through the differential. So this is a special property. If you have a function which is a-differentiable, like that's a very strong condition on the function. There's lots of functions from a norm linear space like A to itself which are not like this. So if this property holds, it's a very, very strong property. Let's kind of investigate how strong it is. So for the sake of making things easier, let's assume that A is equal to Rn. And let's also make that the unity of the algebra is equal to E1. That'll make things a little bit easier in the discussion that follows. All right, so if we think about a function being a-differentiable, then we're thinking about like Rn to Rn is a-differentiable, right? What would that mean about the Jacobian? The Jacobian of f is what? If you don't mind, I'm going to suppress the point dependence for a second here, guys, right? So it was what? It was, I mean, we could write it as what? Partial f, partial x1, partial f, partial x2, right? How many we got? Partial f, partial xn? But, all right, so we're not going to get much insight if we look at it like that. We need to look at it, my definition's in terms of differentials, right? So to gain further insight, we need to switch to differentials. So how do we rewrite partial derivatives in terms of differential? What do we do? Do you guys remember? How about this? We do, at this point, I'm starting to regret not writing the point dependence, but you'll forgive me if I don't. So this is df of E1, df of E2, right? df of En. Yeah? The Jacobian is, after all, the standard matrix of the differential. So to find the first column in the standard matrix, we operate by E1, then E2, all the way out to En. But then there's something special we can do. Because we're assuming it's a-differentiable, we can use that a-differentiability to find there's a very special pattern that has to hold here. So notice that we have df of E1, well, we'll just leave that. There's nothing really to say there. But this one is df of E2, well, E1 times E2, right? Why is that? That's my unity, right? So since E1 is the unity, that means that, E1 times EJ is just equal to EJ for all choices of J, right? But then, all right, because we're assuming that it's a-differentiable, we have the right a-differentiability, so I can pull out multiplication. See, and what I have then is df of E1, df of E1 times E2, df of E1 times En. This means that all of the columns of an a-differentiable function's Jacobian, they're all linked. In fact, they're fixed by the first column. See that? So like we could rewrite this as partial f, partial x1, partial f, partial x1 times E2, so forth and so on, partial f, partial x, 1 times En. And if you tilt your head and squint, you can see what this is going to tell us is that partial f partial xj is partial f partial x1 times ej for j equals to 1, 2, dot, 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 dot. Well, let's not say j equals, do we want to write this equation down for j equals to 1? Let's flag on the play here. Do you care about j equals 1 for this equation? Is that an interesting equation? I mean, it's true. Partial f partial x1 is equal to partial f partial x1. That's lovely, but we don't care about that one. Let's not put that in the list. But if we go from 2 all the way to n, those are the interesting ones, right? These are what are called the generalized Cauchy-Riemann equations. Now, when you guys take, if you have already or maybe not, complex variables, complex analysis here, we study the Cauchy-Riemann equations in the complex setting. Right. So these become the Cauchy-Riemann equations if we look at the complex setting. I'll do that in my next example here. Right. So what does all this mean? What does all this mean? Well, this means that the the Jacobian matrix has a really special form for an a-differentiable function. And so this list of worries I wrote at the start of class about higher derivatives, it starts to vanish in this context. You see, because if you look at this, if I have an a-differentiable function, I can define a derivative as a function again. Let me show you how that goes. So like, well, maybe you can tell me. So I'm given an a-differentiable function, right? So how would you define f prime in this context? I'm claiming that we can define f prime as, again, a mapping from A to A. So the way this works is simply this: we say f prime of z is equal to, well, in the current notation, I guess it's just, I have a bunch of different ways to write it. Golly, I'm trying to think of the way which would be least weird for you guys. We can just say it's this. It's df at z of the one unity for the algebra. This definition of the derivative, it is more general than. Oh, see, that still doesn't. Wait a minute, let me think. Sorry, guys. Yeah, that's fine. This definition doesn't assume, this special. Here we are assuming that E1 was the identity. This would still work when E1 is not the identity. There are other examples where E1 is not the identity. So like the basic thing is, the thing that makes this make sense is the Jacobian matrix is interchangeable with the first column, right? And that is an element of the algebra. So what I'm saying is that because the Jacobian matrix, because the differential of an a-differentiable map is in one-to-one correspondence with an algebra element, that allows us to define a derivative function for an a-differentiable map in this way. Which means we don't run into that whole mess of, higher, like multilinear algebra that I talked about at the start of class. We can just as well talk about, higher derivatives of a-differentiable functions. All right? Like, for example, what example am I on? 5? 5, right? So now this is going to be very, very unsurprising, but if we had f of z equal to z cubed for z in algebra, an a-differentiable function, well, guess what? We can prove the laws of calculus work. In fact, there's a product rule. In my notes, I actually argue from that generalized product rule that I told you guys about, that it follows from that we actually have a product rule for a-differentiable functions. And so using that product rule and some just elementary lemmas, you find out that calculus works just like you expect. And so like f prime of z is, guess what? 3z squared. And f prime prime of z is 6z. And f prime 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 of z is 6. But understand that this calculation I did equally well applies to any of the algebras I've written today. We can formulate calculus over an algebra using this definition and then systematically building the rules of calculus up. I'm not going to put all that on you. That's not this course. But this is interesting for this course because it's an interesting application of like the Jacobian matrix and, well, the definition. Like in order to understand a-differentiability, at the base of it all is the assumption of understanding Fouché differentiability, which is our definition of real differentiable in here. So if you want to know more about a-calculus, I would be happy to tell you more if you're interested in. And I've written a primer for undergraduates to understand. It's about 40, 50 pages long. In that primer, I develop all of the rules of calculus I'm telling you work, and a multitude of additional examples and so forth. So if you're interested, ask me. I can show it to you. In the time that remains, though, I want to show you something actually really interesting that I found with a student. And this is actually about differential equations. So some of you have had differential equations, some of you have not. But I'm going to show you a method to solve differential equations which is universal. I can solve literally any constant coefficient differential equation with one method. All right? And so the method is this. So do you guys know what a constant coefficient differential equation is? What's that look like? Okay, so yeah, I mean, I'm almost with you. We're going to assume that the leading coefficient is 1 just for the sake of not writing as much. But suppose we've got like, the nth derivative, right? Plus a sub n minus 1 times the n minus 1th derivative plus plus, a2 times y prime prime plus a1 times y prime plus a sub 0 times y equals to 0. This is the nth order homogeneous differential equation. So a problem I set out to solve with a student a few years ago was how could I solve this differential equation if the derivatives are not real derivatives, but they're algebra derivatives? Can I solve this differential equation over an arbitrary associative algebra? Is it possible? How would it be done? And after the dust settles, we've learned a method that actually will solve a differential equation not just over any algebra, but also in the regular course. So rather than tell you the general method, I'm just going to illustrate it by example. All right. So let's go. So example 6. Suppose I wanted to solve. We'll start out really easy, which is this one: y prime prime equals to 0. Right. So what I do is I look at the algebra I use to solve this differential equation. Is I use basically real polynomials, let's say I'll use k for the variable, and I divide by, I take the quotient by what's called k squared. And so what this means is that k squared is equal to 0 in this algebra. This algebra makes k squared be 0. It turns out in any algebra you can write down an exponential in the algebra like this. So what I do is I take an exponential in t times k. So you know how the exponential works. What's the rules for exponentiation? So this is like, 1 plus tk plus 1/2 tk squared, right? Plus dot dot dot. Of course, tk squared we could also write as what? We could write it as t squared times k squared, right? And then the next thing would be like 1 over 3 factorial t cubed times k cubed. You know the exponential series, I hope. But what did we just say about this algebra? This is the algebra in which k squared is 0. So what happens to this power series? How about this here? All 0. All right? So I look at this, and the coefficients of 1 and k are, I'm going to write it down this way, y1 is equal to 1, and y2 is equal to t. This is not an accident. If you've had differential equations, or, well, forget differential equations. If you've had calculus 1 and you know how to integrate an equation 2 times, right? You know that the solution to this differential equation is what? C1 plus C2 times t. So that's the general solution here. I have obtained the fundamental solution set, though, understand it, as the coefficient functions of the exponential of the algebra in what I call the characteristic algebra. I call this the characteristic algebra. It's the algebra which is characteristic to the differential equation. Let me show you another. This is not particularly impressive because everybody can integrate twice and solve y prime prime equal to 0, right? I hope. Not a big deal. What if we have y prime prime plus y equal to 0? Right? Y prime prime plus y equals to 0. Let's look at that. Example 7. Y prime prime plus y equal to 0. So this time, my characteristic algebra looks like A. I take, polynomials in K, and I work subject to the modulo, the condition k squared plus 1. Right? So in this algebra, this means that k squared plus 1 is equal to 0, or if you prefer, k squared is equal to minus 1. Again, I will do the same thing I did last time. To find the solution to this differential equation, I will consider the exponential of t times the generator for the algebra. Okay, e to the tk. Again, I will rewrite this as the sum n equals, well, not, actually I'm going to do something rather radically different here. Sum n equals 0 to infinity of, t to the n over, my bad, t to the 2n over 2n factorial, k to the 2n, plus the sum n equals 0 to infinity of t to the 2n plus 1 over 2n plus 1 factorial, k to the 2n plus 1. I can do this, right, because the exponential series is, well, sidebar, we've also proved calculus 2 works. So the theory of convergence of series over a complex algebra, over an associative algebra is also a sensible thing. So these calculations are reasonable. But all I'm doing is I'm breaking up the exponential series into its even and its odd terms, right? Now, if k squared is minus 1, k to the 2n is equal to minus 1 to the n. And k to the 2n plus 1 is equal to minus 1 to the n times k, which gives this as the sum n equals 0 to infinity of, minus 1 to the n t to the 2n over 2n factorial plus, I'll pull the k out, sum n equals 0 to infinity minus 1 to the n t to the 2n plus 1 divided by 2n plus 1 factorial. Can you recognize what we have? What are we looking at here? Cosine and sine, yes. This here is cosine t. This here is sine t. Those are the fundamental solutions to this differential equation. So by the same method, I write down general solution, c1 cos t plus c2 sine t. I've solved this differential equation with complex characteristic equation, to use the language of differential equations. I solved it in the same way I solved the repeated real case. Let's do another. We can do this all day. So by the way, in that case, the characteristic algebra is what? Up to like notation. What is this characteristic algebra? What's an algebra which is defined by things that have a square to go to minus 1? What is that? That's the complex number system. So the complex numbers is what gives us this solution. Example 8. If we were to look at, say, y prime prime minus, I'll mix it up minus y equals to 0. We would then be looking at e to the tk, and it would work out to, guess what? Cosh t plus k times sinh t, where here k squared is equal to 1. In this case, the solution is c1 hyperbolic cosine of t plus c2 hyperbolic sine of t. In this case, I would argue that the characteristic equation for this problem is the hyperbolic numbers. The component functions to the characteristic exponential are hyperbolic sine and cosine. In the previous example, the characteristic functions to the exponential of the algebra were sine and cosine. Yeah. And we can play these games all day long. Let me bump it up a notch here. Example 9. What if we're studying, say, y prime 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 minus y equals to 0? This is a third order differential equation. All right? Yeah? This is the Three Stooges, yes. You've seen through my plan. So this has characteristic, though the characteristic algebra here is k cubed minus 1 equals to 0, right? If you like, I could just change the k to a j, but anyway, so here, if we look at the characteristic exponential, e to the kt, we've got like the sum n equals 0 to infinity of t to the 3n over 3n factorial plus k times the sum. Through a calculation very much like the one I already did, but notice that there's no minus here because we just have k cubed equals to 1. And then the calculation I'm doing, it follows from the fact that integers can be partitioned into either multiples of 3 plus 1, or multiples of 3 plus 2. These are distinct categories of integers. And so, yeah, that happened. Yep.
What if it's not homogeneous?
Ah. Well, that would be a different problem. But what if it's not homogeneous? I said any homogeneous constant coefficient problem I can solve. But yeah, I can solve those too. Yep.